Have you ever wondered why you can't just walk through a wall? Why matter is solid? The answer lies in one of the most fundamental and powerful rules in the universe, the Pauli Exclusion Principle. Formulated by the brilliant physicist Wolfgang Pauli, the principle is surprisingly simple. It states that two identical fundamental particles called fermions cannot occupy the same quantum state at the same time. Think of it like assigned seating in a cosmic theater. Every electron, proton, and neutron has its own unique ticket. Inside an atom, this means no two electrons can have the exact same set of quantum numbers, which are like their unique address and spin direction. This forces electrons into different energy levels, or shells, creating the atomic structure that underlies all of chemistry and the periodic table. This is the reason matter takes up space and feels solid. It's the universe's way of saying, no trespassing on a subatomic level. And here lies a stunning paradox. Despite this feeling of solidity, an atom is almost entirely empty space. If the nucleus of an atom were the size of a marble placed on the center of a football field, the nearest electrons would be like tiny specks of dust whirling around the outermost seats. The vast expanse in between is empty, so the solidity you feel isn't from matter being tightly packed. It's the powerful no trespassing rule of the Pauli principle, acting across this emptiness, that creates the impenetrable force fields we perceive as a solid surface. But this principle does more than just build our world. It operates on a scale that is almost impossibly grand. When a star much more massive than our sun dies, it collapses under its own colossal gravity. The pressure becomes so immense that it overcomes the forces separating atoms, smashing electrons and protons together to create a super-dense ball of neutrons. This is a neutron star, an object with the mass of one or two suns, crushed into a sphere the size of a city. So what stops gravity from crushing it all the way down into a black hole? The Pauli Exclusion Principle. The neutrons, being fermions, are now subject to this rule. As gravity tries to squeeze them into the same space and energy state, the principle says no. The neutrons are forced into higher and higher energy levels, creating a tremendous outward pressure. This is called neutron degeneracy pressure, and it is the only thing standing against the star's complete gravitational collapse. This quantum pushback is powerful enough to support the entire, unimaginably dense star. The Pauli Exclusion Principle is a true cosmic architect. A less extreme version, called electron degeneracy pressure, is what supports the remnants of smaller stars, the white dwarfs. So, from the shape of atoms and the diversity of chemical bonds to the very existence of some of the most extreme objects in the cosmos, this one quantum rule is at work. It's a profound reminder that the largest structures in the universe are often governed by the smallest, most fundamental laws of nature. The Pauli Exclusion Principle doesn't just keep your hand from passing through a wall, it holds up the stars themselves. The world around us feels solid, stable, and real. It's all made of atoms, which are themselves made of protons and neutrons. And inside them we find the fundamental building blocks, up and down quarks. This is normal matter. For all of history, we believed this was the ultimate ground state of the universe, the most stable, most fundamental way matter could exist. But what if it isn't? What if our universe is living in a fragile, metastable state, and there's something far more stable and far more dangerous? Deep inside the cosmic crush of a neutron star, the laws of physics are pushed to their absolute limits. Under pressures we can barely imagine, protons and neutrons dissolve into a dense soup of their constituent quarks. Here, something remarkable can happen. The intense energy can cause some of the up and down quarks to transform into a heavier, more exotic type, the strange quark. This gives rise to a new hypothetical substance, strange matter, a dense liquid made of roughly equal numbers of up, down, and strange quarks. According to the strange matter hypothesis, this three-quark configuration could be the true ground state of matter. It's more stable than the protons and neutrons that make up you, me, and everything we've ever known. The matter of our entire universe might be like a diamond, waiting for the right stimulus to collapse into something denser. If this hypothesis is true, then small, stable fragments of this substance, called strangelets, could exist. They could be forged in the collision of two neutron stars and flung across the cosmos. And this is where the theory becomes terrifying. A strangelet is predicted to have a unique and devastating property. Because it is more stable than normal matter, any atomic nucleus it touches would be converted. Upon contact, the strangelet would begin to absorb the neutrons and protons, rearranging their quarks into the more stable strange configuration. The process would be catalytic, turning normal matter into more strange matter and releasing a burst of energy. This is the Ice-9 scenario, named after the fictional substance in Kurt Vonnegut's novel Cat's Cradle. In the book, a single crystal of Ice-9 could freeze the world's oceans. A single strangelet could, in theory, do something far worse. If a single, stable strangelet were to strike the Earth, it could start a chain reaction. It would consume our planet from the inside out, converting it atom by atom into a hot, dense sphere of strange matter just a few dozen meters across. Everything we are and everything we've ever built would be annihilated in a flash. Now, physicists believe this is an extremely unlikely scenario. Most models suggest that strangelets created in space would be unstable or positively charged, repelling them from atomic nuclei. Experiments on Earth have not produced any stable strange matter, and the fact that the Moon and Earth are still here after being bombarded by cosmic rays for billions of years suggests we are safe. But the hypothesis remains. In the vast, dark corners of the universe, there may be a form of matter so perfect, so stable, that it would instantly and effortlessly erase our own.